In this class, we will show you how to use VLANs and Fortigate virtual domains. VLANs and VDOMs are not directly related. Multiple VLANs, for example, do not define a VDOM. However, they are both in this class. They are often used together if you route traffic from multiple companies or divisions through the same Fortigate. For example, if you're a large university, you may want to assign a network administrator for the accounting department to configure the firewall policies governing that department, but not allow them to affect other departments. Relatedly, you may want all accounting offices to be on the same virtual LAN, even though they are located in physically separate buildings. Here's an overview of what we will discuss. Essentially, we will talk about two methods that you can use to separate and join traffic into logical domains that might be handled by separate administrators, for example, or separate security policies. We will also discuss how to route traffic between two of these logical domains. Note the capital letter V because we're not talking about VLAN adapters on virtualized machines such as VMware or Xen. VLANs are created when we configure a network interface that corresponds to a physical NIC port such as port 1 or port 2 to subdivide traffic based upon tags found in the Ethernet frame. When we do this, the frame has more than just a MAC address that we can use to map to an IP subnet. Let's see the difference. Above shows a plain Ethernet frame. It contains MAC addresses for the physical adapters that are sending and receiving the frame, the type, the data payload that in this case will contain the IP layer, and finally a CRC code that helps to ensure noise hasn't corrupted the frame data. The diagram below shows an Ethernet frame that complies with the 802.11q VLAN standard. Notice that it has 4 more bytes in the middle. In the diagram before, we showed that VLANs add 4 bytes to each frame. What are they used for? They have an identifying number. Regardless of which physical port transmitted or received the frame, if the frame has the same VLAN ID tag as another, it can be organized into the same virtual LAN. Fortigates can add and act on this ID. Notice that VLAN IDs are not authenticated nor encrypted. Their original design was to improve LAN performance by providing a way to prevent unnecessary frame retransmission. Many people think that VLANs are a security measure, but the VLAN standard provides no mechanism to guarantee that the ID has not been maliciously altered and shouldn't be inherently trusted. To guard against VLAN spoofing, physically secure switches and routers. Also consider features such as reverse path forwarding. Strictly speaking, VLANs aren't secure on their own. They simply define logical LANs. When operating in NAT route mode, Fortigate is, among other things, a layer 3 router. So it can do more than a layer 2 switch. That is, it doesn't just remove VLAN tags from frames being forwarded to destinations and add VLAN tag frames being forwarded from the source. Fortigate can also rewrite VLAN tags. Before Fortigate forwards a frame, if you've configured it, Fortigate will change the VLAN tag. This allows it to arrive at a destination that belongs to a separate VLAN. In contrast, if Fortigates were only a VLAN switch, it would not forward it to any other VLANs. The packet would be dropped. In the example above, a computer sends a frame which passes through a router first. This router applies a VLAN 100 tag since the frame originated from a computer on VLAN 100, not VLAN 200. Then, the router forwards to the network interface on the Fortigate that is also configured as part of VLAN 100. Then, the Fortigate is configured to route from VLAN 100 to VLAN 300. Fortigate removes the VLAN 100 tag and matches the packet with a firewall policy. Since the packet is acceptable and is destined for an address on VLAN 300, Fortigate rewrites the VLAN ID to VLAN 300 before forwarding it to the next router. The last router removes the VLAN tag because this is the last hop, then forwards the frame to its final destination. Note that all devices on your VLAN paths must support VLANs. When configuring Fortigate, the VLAN tag in the frame will be exactly what you configure. On other vendors' devices, this may differ. In this example, computers located in separate buildings are part of the same department, accounting. They often share files, which results in much traffic. But notice the other computers in each subnet. They are not part of accounting. They are connected to the same switch only because they are located in the same room, not because they are logically related. They shouldn't be bombarded with frames from accounting computers. To prevent broadcast collisions with neighbors, we would connect network cables from each of these three accounting computers to their own switches in order to create a distinct physical LAN. Instead, the network administrator here has configured Fortigate and other devices to VLAN tag the frames from accounting computers. This causes frames to be forwarded only to devices in the same VLAN. To route a packet to another VLAN, the frame must reach a Layer 3 router, such as Fortigate, which can rewrite the VLAN tag. So far, we've seen network segments subdivided and unified. It was one organization with a single set of policies and a few administrators. In effect, a single security domain. What if you are an MSSP? What if you are a very large company? What if you want to subdivide policies and administrators into multiple security domains? In that case, you can enable Fortigate VDOMs. Each VDOM has its own interfaces, which can be real or virtual. It also has its own routing tables, firewall policies, packet inspection, and so forth. In that way, enabling VDOMs causes your Fortigates to behave as if they were multiple smaller Fortigates. Due to hardware differences, the maximum number of VDOMs varies by model. For models with greater hardware capacity, you can purchase a license to allow more VDOMs. Configure this with care. Due to shared hardware, the total number of sessions, etc., for all VDOMs will impact performance. Next, let's see how you can fine-tune VDOM resource allocation. Remember, VDOMs are a logical separation only. Each VDOM shares physical resources with the others. Unlike with Fortigate VM, VDOMs are not allocated and balanced with weighted vCPU cores, VRAM, and other virtualized hardware. To fine-tune performance, you will configure resource limits for each feature, IPSec tunnels, address objects, etc., at both the global level and for each VDOM. This controls the ratio of each VDOM's system resource usage to the total available resources. For example, on this Fortigate, the hardware is powerful enough to handle up to 2,000 IPSec VPN tunnels. The Fortigate is configured with 3 VDOMs. VDOM 1 and 2 don't use IPSec VPN tunnels often and are allowed to have up to 50 each. VDOM 3, however, uses VPN extensively. Therefore, this Fortigate will be configured to allow VDOM 3 to have up to 1900 tunnels. Additionally, 1,000 of these tunnels will be guaranteed. Configure your Fortigate with total limits for critical features such as sessions, policies, and others. Then configure each VDOM with its own quotas and minimums within the global limits. Global resource limits are an example of global settings. The firmware on your Fortigate and some settings, such as system time, apply to the entire appliance. They are not specific to each VDOM. Most settings, however, can be configured to be different for each VDOM. To enable VDOMs when you are logged into the GUI, in the System Information widget on the dashboard, in the Virtual Domain row, click the Enable link. This won't reboot your Fortigate, but it will log you out. Enabling VDOMs restructures both the GUI and CLI, which you will see when you log in again. Alternatively, to enable VDOMs when you are logged into the CLI, enter this command. Again, you'll see the new structure of the CLI and GUI when starting your next administrative session. After enabling VDOMs, by default, only one VDOM exists, the root VDOM. It's the management VDOM, which we will discuss soon. You need to add a VDOM for each of your security domains. If you're an MSSP, for example, you might add one VDOM per client company. If you're an enterprise business, you might add one VDOM for each division of your company. Remember that, as described before, you also may need to adjust each VDOM's resource allocation. If you log in as most administrator accounts, you will enter your VDOM automatically. But if you were logged in as the account named admin, you aren't assigned to any VDOM. To enter a VDOM on the GUI, click the Virtual Domains part of the menu. Inside, you will see the default VDOM named root. This is the management VDOM, which we will see more of soon. Other VDOMs that you can configure will also appear under the Virtual Domains menu. To access a VDOM, click it and expand its contents. Inside each VDOM, the submenu should be familiar. It is essentially the same navigation menu that you had before you enabled VDOMs, except that the global settings moved out to the global part of the menu. Access to VDOMs isn't the only change to the GUI and CLI. How does enabling VDOMs change the structure? Settings that apply to the entire Fortigate are split apart from settings that can be configured individually for each VDOM. Administrator privileges also change. For example, by default, while VDOMs are enabled, some CLI commands are available only to the admin account while within the config global shell. The admin account is the only account that isn't assigned to a specific VDOM, and so it is the only one that should be able to configure global settings. Note that you can grant access to multiple VDOMs if you assign. Other CLI commands are available to any administrator, but only from within a subshell such as config VDOM, edit VDOM 1, because they are specific to that VDOM. The same permissions that apply to the GUI and CLI also apply to backups. We'll talk more about VDOM administrators in a minute. For now, let's see how you enter a VDOM. In most cases, you'll start by creating one administrator account per VDOM. He or she will be chiefly responsible for that VDOM, including that VDOM's configuration backups. In larger organizations, you may need to make more VDOM administrators. Multiple administrators can be assigned to each VDOM. You can subdivide their permissions using access profiles in order to follow best practices for segregation of duties. The converse is also possible. If required, you can assign an administrator to multiple VDOMs. If you want to grant access to all VDOMs and global settings, select Super Admin as the access profile when configuring the administrator account. Similar to the account name admin, this account will be able to configure all VDOMs. Best practice dictates that you usually should avoid unnecessary security holes, however. Do not provide super admin access if possible. Instead, restrict each administrator to their relevant domain. That way, they cannot accidentally or maliciously impact other VDOMs, and any change or mistake will be limited in scope. Similar to when you create new VDOMs, when you create new administrator accounts and assign them to a VDOM, access it through the global part of the navigation menu. To review, each VDOM behaves as it is on a separate Fortigate appliance. With separate Fortigates, you would normally connect a network cable and configure routing and policies between them. But VDOMs are on the same Fortigate, so how should you route traffic between them? The solution is inter-VDOM links. With inter-VDOM links, you won't send traffic out through a physical cable or VLAN, then back into the same Fortigate to reach another VDOM. Inter-VDOM links are a type of virtual interface. Note that, like with inter-VLAN routing, Layer 3 must be involved. You cannot create an inter-VDOM link between Layer 2 transparent mode VDOMs. At least one of the VDOMs must be operating in NAT mode. This means its network interfaces will have an IP address. Destination addresses and gateway IPs are required by routing with the IP protocol. It also prevents potential Layer 2 loops. When creating inter-VDOM links, you'll need to create the virtual interface, but you also must create a matching firewall policy, just as you would if the traffic was arriving on a network cable. Otherwise, Fortigate will block the traffic. In the menu, creating a network interface is located in the global settings. To create the virtual interface, click the drop-down menu arrow, then choose VDOM link. Up until now, we've discussed traffic passing through Fortigate from one VLAN or VDOM to another. What about traffic originating from your Fortigate itself or destined for it? Administrator sessions and system daemons such as NTP and FortiGuard updates generate this kind of traffic. When VDOMs are enabled, this means that a special VDOM named root must be automatically created so that the Fortigate has network interfaces that can continue to send and receive system-related packets. Similar to a Fortigate without VDOMs, the root VDOM usually should have outgoing internet access. Otherwise, features such as scheduled FortiGuard updates will fail. There are a few ways you can arrange your VDOMs. In this topology, each network accesses the internet through its own VDOM. Note that inter-VDOM traffic is not possible unless it physically leaves the Fortigate towards the internet and is rerouted back. This is most suitable for multiple customers sharing a single Fortigate, each in their own VDOM with physically separate ISPs or large pipes, for example. Notice that there were no inter-VDOM links in the previous example. Traffic flowed to the internet through completely separate physical links. This is another example. Like the previous topology, each network sends traffic through its VDOM, but after that, traffic is routed through the management VDOM, by default named route. So internet-bound traffic flows through a single pipe in the route VDOM, and if route VDOM policies allow it, inter-VDOM traffic is not required to physically leave the Fortigate. This could be suitable for multiple customers sharing a single Fortigate, each in their own VDOM. But in this case, the management VDOM could log and monitor traffic and/or provide standard services like antivirus scanning. Since traffic would not be scanned twice, one during egress, the second during ingress, in some cases it could improve performance compared to the previous example topology. Note that this topology has inter-VDOM links, but peer VDOMs are only linked with the management VDOM, not with each other. In this case, VDOM's traffic flows through the same physical link, the one belonging to the management VDOM. Inspection could be done by either the root or original VDOM, depending on your requirements. Alternatively, you could split inspection so that some scans occur while traffic is in the root VDOM, ensuring a common security baseline, while more intensive VDOM-specific scans can optionally occur in the originating or destination VDOM. Here, traffic again flows through a single pipe in the root VDOM towards the Internet. Traffic between VDOMs doesn't need to leave the Fortigate. However, it also doesn't need to flow through the management VDOM either. Inter-VDOM links between peer VDOMs allow more direct communication. Like the previous example, inspection could be done by either the root or original VDOM, depending on your requirements. Due to the number of inter-VDOM links, this example is the most complex, requiring the most routes and firewall policies. Troubleshooting meshed VDOMs can be more time-consuming. However, meshed VDOMs also provide the most flexibility. For large businesses, inter-VDOM communication may also be required, and inter-VDOM traffic performance may be better due to a shorter processing path which bypasses the management VDOM. Now it's time for the labs. In this lab, you'll enable VDOMs, then create a VDOM and assign administrators to it. You'll also route traffic through your new VDOM. In this class, we will show you how to configure Fortigate to operate in transparent mode and discuss differences with NAT mode. We will teach you how to make a decision that is fundamental to your entire Fortigate configuration. Which operation mode should you choose? Most people are familiar with firewalls operating as NAT devices, which hide the IPs of your private network. But in transparent mode, Fortigate forwards packet as a non-NAT device that doesn't usually hide IPs. Due to this, configuring transparent mode is slightly different. It has unique benefits and drawbacks. So we'll explore both the features and special considerations of transparent mode. We'll discuss when it's appropriate to use NAT and when it isn't. We will also show you how to configure some features, such as STP, VLANs, and VDOMs that are configured slightly different in transparent mode, and how to avoid some common mistakes. What do we mean by transparent? Is it the same as hidden? Can the client detect the Fortigate? No, they aren't the same. Although detection is slightly more difficult, a transparent Fortigate isn't totally invisible. Here, transparent only means that at the IP layer, clients can see through your Fortigate. A transparent mode Fortigate forwards packets without changing IPs. When the client receives a packet from a server behind a Fortigate, the packet contains the server's real IP, Fortigate doesn't rewrite the IP header, so the server's address and listening socket isn't masked. Likewise, in the other direction, clients send packets directly to the server's real IP address. Fortigate is a layer 2 bridge or switch. How is that different? Traditional IPv4 firewalls and NAT mode FortiGates are routers, not just switches. FortiGate virtual IPs also apply NAT, which does change the destination IP and sometimes the port number to hide your network architecture from clients. Source NAT too can hide the opposite direction, client IPs from servers. Transparent mode by default doesn't do either. So large organizations benefit. They usually don't want to reconfigure thousands of devices to define a new internal versus external network. They also may have dedicated routers that are separate from Fortigate. By the way, NAT has a side effect: you can join your whole internal network behind one IP on the Internet. IPv4 addresses on the Internet are few. Often, to get more public IPs, you must buy them from your ISP. So NAT lowers costs. But if you're deploying Fortigate as an internal rather than edge firewall, the external IP is to other parts inside your own network. You don't have to pay your ISP for that. So NAT doesn't benefit internal firewalls as much. Cost benefit doesn't apply in pure IPv6 networks either, since it supports many more public IPs. So those are cases where you might consider transparent mode. Always carefully plan and choose the operation mode. If Fortigate has already been deployed, this will disrupt your network while you reconfigure. But for larger networks, broadcast storms are possible and can disrupt the entire network until you configure forwarding domains. We'll show more about forwarding domains soon. First, let's see the difference between NAT and transparent topologies. Here is an example showing NAT. Fortigate has 3 connected ports, each with separate IP subnets and routes. All interfaces on the Fortigate have an IP address, and NAT translates between networks. Firewall policies allow traffic to flow between networks. Fortigate forwards packets according to either static routes, which are based on the destination IP address at layer 3 of the OSI model, or other IP-based routing rules such as policy routes and dynamic routes. Clients on each subnet send packets that are destined for a Fortigate virtual address, not the real address of the server, and Fortigate rewrites the destination IP and/or port number to the real one before forwarding the packet. Reply packets are rewritten to replace the real source with the virtual. Here's an example showing transparent mode. Firewall policies still scan, then allow or block traffic, but everything else is different. First, only 2 Fortigate ports are connected, a port pair. Second, notice the physical interfaces on Fortigate have no IPs, so Fortigates won't respond to ARP. There are only 2 exceptions. When changing to transparent mode, you can specify a port that will receive connections from your network administrators and send log messages, SNMP traps, alert email, HA signals, and so forth. That is, management connections. You can configure individual interfaces with an IP to also apply NAT or PAT. Note that this is rarely required. NAT with transparent mode is usually a misconfiguration. Either Fortigate isn't positioned correctly in your topology, or the appropriate operation mode wasn't chosen. By default, a transparent Fortigate won't do NAT. Unless an upstream router applies NAT, which you see here, clients will send packets destined directly for the server's IP. Lastly, notice there are no routes. This is because Fortigate is forwarding based on frames like a switch or bridge, layer 2 of the OSI model, not IP packets like a router. First, let's talk about the physical difference between the examples. Only 2 ports were connected in transparent mode, one to the internal network and another to the external. Policies forwarded traffic between those 2 ports only, never involving another port. Effectively, they were bound, acting like a filtered pipe. Why? Port pairing isn't required. Just like in NAT mode, you can use more than 2 interfaces and forward between any. But port pairs are the easiest topology to configure correctly. Otherwise, you must plan to prevent layer 2 problems such as broadcast storms and loops. You might need to configure more. We'll show some of these problems and solutions later. You could make more than 1 port pair as well. Here's an example where 2 port pairs are used. This Fortigate has 4 ports, each connected to different physical locations, but traffic is not allowed to flow between all 4 locations. Policies only allow traffic between ports in the same pair, between port 1 and port 2, and between port 3 and WAN 1. So in this example, the network on port 3 can reach the internet through WAN 1, but the networks on port 2 and port 1 can't reach the internet. They can only reach each other. Next, let's talk about the second difference between NAT and transparent examples, the IP addresses. By default, transparent interfaces have no IP address. Instead, Fortigate forwards if the frame is destined for a MAC address that the Fortigate knows. With a port pair, frame forwarding is simple, from one link peer over a Fortigate bridge to the other link peer. But what if you don't have simple port pairs? What if you have branching? What if you have redundant links, creating layer 2 loops? Or what if there are other layer 2 switches on your network? There could be more than one path to the same MAC. Design of layer 2 of your network becomes crucial when you have multiple segments connected. To ensure correct frame delivery, different devices must not have the same MAC address. If there are multiple paths to one MAC address, you must configure your network to temporarily disable forwarding along most paths so that, for example, Fortigate doesn't deliver multiple ARP requests to the same device. Finally, for best performance, you'll want to always use the shortest viable path. You can configure this manually, but in complex networks, it's easier and faster to manage links and MAC-based forwarding via a layer 2 protocol such as STP. Spanning tree protocol automatically ensures that there are no layer 2 loops. By default, Fortigate does not participate in STP learning, nor forward BPDUs, but you can enable it. You must still restrict broadcast domains so that they are not overwhelmingly large, though. We'll talk about that next. With port pairs, you could only forward BPDUs, but with branching, you should configure Fortigate to participate. To enable STP globally, use the config system STP command in the CLI. To configure STP on each interface, use the set STP Forward command while inside config system interface. Note that this is only supported on models with switch interfaces such as Fortigate 30D, 60C, 60D, 80C, and 90D. So now we've solved layer 2 loops. what about broadcast storms and MAC flapping? At the beginning, we said to choose your operation mode carefully before configuring forwarding domains. This is very important with VLANs and VDOMs, features often used in large networks. In transparent mode, by default, each VDOM has a separate forwarding domain. Interfaces, though, don't. How does this affect branching topologies? Until you change the initial VDOM configuration, all interfaces connected through firewall policies are part of the same broadcast domain. Fortigate will broadcast from every interface in the VDOM in order to find the destination MAC address. On large networks, this could generate massive broadcast traffic and overwhelming replies, a broadcast storm. And as mentioned, you can't reconfigure the scope of the forwarding domain while it is referenced by address objects, firewall policies, or other parts of the configuration. So it's crucial that you configure it correctly before you deploy. Here's an illustration of the problem. A broadcast with an unrestricted forwarding domain. An ARP whois is sent by a single device. It reaches Fortigate through one of the interfaces in the VDOM. Because they all belong to the same forwarding domain, Fortigate then rebroadcasts to all interfaces. This generates a lot of traffic, but in theory, the ARP reply still will arrive on only one interface, and Fortigate will learn that the MAC is on that interface. However, what if there is more than one path? Fortigate would rapidly switch between links because the last interface that receives an ARP reply with the MAC address will vary slightly. This will cause transmission problems. The three-way TCP handshake involves 3 packets, and if the IP session is transferred from one interface to another in the middle of transmission, the handshake will fail. Another way to restrict the scope of broadcast forwarding is to configure VLANs. Fortigate can be an IEEE 802.1q VLAN trunk in transparent mode. Here are VLANs with a transparent Fortigate. Traffic originates here on a computer and is sent to switch A. The switch tags it with VLAN 100 and sends it to switch B. In between switch A and switch B, you have a transparent Fortigate. It has interfaces with VLAN 100 and firewall policies to allow the traffic. This network was set up prior to deploying a Fortigate, so Fortigate has been deployed transparently to avoid the need for changes to the network. Once traffic reaches switch B, it removes the VLAN tag and delivers it to the destination computer. Forwarding domains are like broadcast domains, but for VLANs. When a VLAN frame arrives, Ethernet headers are stripped. The packet is inspected. Upon egress, headers are added again. Because forwarding depends on OSI layer 2, not layer 3, unless you properly separate your networks, Fortigate could accidentally send frames in the wrong direction. Here, the same network that we showed before for VDOMs, but here, VLAN 101 is only on 2 interfaces. Placing them in the same forwarding domain ID segregates them. Traffic arriving on one interface is only broadcast to interfaces that are in the same forwarding domain. If Fortigate knows the destination is on a separate network, a packet can cross to different forwarding or broadcast domains if a firewall policy allows it. Now it's time for the labs. In this lab, you'll create a VDOM that is configured for transparent mode. You'll also create an inter VDOM link between the transparent mode VDOM and a NAT mode VDOM.